Hi, everyone, and welcome back to my next installment of this algebra and pre-calculus series. In this video, it's going to be a continuation of the last one. We're going to be sticking with quadratics, um, specifically quadratic functions. Now, you see quadratic expression on the screen right now. Assuming you've watched all of the videos leading up to this one in the playlist, um, we've talked about quadratic expressions. We talked about them early on. Now, a quadratic expression, remember, expressions do not have equal signs. So any expression of the form ax squared plus bx plus c, where a and b and c are any real numbers. Now we're specifying real because we just talked about complex numbers in the previous video. But so a, b, and c have to be real numbers, and a can't be zero. If a was zero, there would be no x squared because it would be 0 times x squared. So a can't be zero, but it could be anything else, and b and c could be anything. Quadratic expressions. So we've talked about them. And then I think next in line, we talked about quadratic equations. So that's just with a equal sign, makes it an equation. So to go from here to here, we just throw in a equals 0. Now we can start talking about solving, right? You can't solve an expression. You can graph. I didn't actually want to talk about graphing yet. No, we don't even graph those. We talked about, let's see, we could factor. Yeah, that's one thing we could do. A couple other things. Solving is one thing we could do with an equation that we can't do with an expression. And when we solve an equation like this is something we've used in a number of previous videos of mine on this playlist. We have the quadratic formula. So it's like an if-then statement. If you've got an equation that looks like this, then you've got answers that look like this. If-then. Now, you may not get any answers. You may get one, you may get two, if you're restricted only to real numbers. But if you're allowed to use complex numbers, you'll never get no solution. It'll always be two answers. Either it could be the same number repeated twice, or two different numbers, complex numbers, potentially quadratic equations. We talked about solving quadratic equations in a number of my videos, including the one just before this one. Here, we're going to talk about quadratic functions. Right, so there is no more solving. Solving is a concept that is unique to equations, right? So we have an equation up here. We have a function down here, right? With an equation, we have left side equals right side. We have two sides of an equation. Right, with a function, we have one expression, and the name of this function is the f function. And so this ax squared plus bx plus c, which we've seen in the context of expressions and equations, now we're talking about it in functions, this is called the general form, Now, we could manipulate this to make it look differently. We did this with linear equations. We saw point slope form, we saw slope intercept form, we saw general form, through ways of doing the same thing or saying the same thing. Same thing here. We could take, let me erase some of this because we don't need that. We're just talking about, in this video, we're just talking about down here, functions, quadratic functions. We've already talked about the previous two. But this is not a new topic, a new concept completely. We're going to still need to do things like factor and solve and use the quadratic formula and things like that. Now, you can take what's called the general form. So let me just write that up here. General form. And you can just make it look differently, manipulate it to look slightly differently. And this is called the standard form. General form, standard form. It's like with lines, we have slope intercept and point slope form, two different forms, but we could we could express the same exact line two different ways. Same thing here. We could the same parabola, the same graph, the same solutions, just two different forms. Now, to go in this direction, see my blue arrow connecting them to go from here, general form, to here, standard form. The way you do that is something which unfortunately I skipped in this particular course that I'm teaching. So it's not hugely important. Decided to spend our time on other things, but it's a method called completing the square. So we'll just say complete the square. That's how you go from general form to standard form. And if you want to go in the other direction, that's something that we've for sure spoken about. Multiply. And in this case, it would be FOIL, because we have a minus h x, or x minus h parentheses square. So you would have to FOIL, you distribute, collect like terms. We'd do all three. Right? We would just multiply and collect, or let's say combine. I think combine is a better word. Combine like terms. Okay, but we don't need to go back and forth in the, for all intents and purposes in this class, in this lecture. So I want to focus on how each of these forms is connected to the graph. Right? Because we've seen the graph of a quadratic function before. Right? We talked about transformations, shifts, left, right, up, down, right? Stretching, compressing, reflections over the x-axis, reflections over the y-axis, reflections over the origin. We've talked about all different ways of transforming a graph. So we're not going to take that same approach here. We're going to talk about, I'm going to erase everything that's on here because I want to focus on what's going to be relevant for this specific set of problems. And that's graphing. So every quadratic equation or quadratic function has a graph, as long as the equation is y equals, not equals 0. That's just going to give you a couple of numbers. But y equals, or f of x equals ax squared plus bx plus c. The graph is going to be a parabola. It's either going to be pointed up or it's going to be pointed down, depending on the a, right? Ax squared plus bx plus c, or a times x minus h squared plus k. If a is a positive number greater than 0, the parabola is going to be pointed up. If a is a negative number less than 0, it's going to be pointed down, and a can't equal 0. So it's either greater than or less than. If you have a quadratic function that's in general form, then the vertex of that parabola, the vertex is that central point that if you drew a vertical line splitting the graph into two equal halves, you would cross through that point, that vertex. Let me actually label it up here. We'll say vertex, a little arrow, and vertex. Right there. So that central point, that vertex, is the point. Now you could look at this as being a formula that you have to know. For example, in my class, the tests are open notes, so you don't have to remember it necessarily, but you have to be able to use it, reference it, bring it up when you need it. So have it either written down or committed to memory. So it's the point negative b over 2a for the x value, remember every point is an x comma y. All right, so what this is saying is that the vertex, let me go back to a different color, maybe black. The vertex is a point x comma y. So the x value is negative b over 2a. And the y value is f of negative b over 2a. So you figure out the x value first, and then you plug that into the function to get the y value. Now, if you are working with a function in standard form, now notice it's the same a. So the a in that blue box and the a in that green box are the same number. The b and the c don't appear twice. So the b and the c are only in the blue one. The h and the k are only in the green one. So those numbers are different or potentially different. If you have an equation or a function in what's called standard form, this one's easier to work with because you don't have to do any calculations. You just read the numbers directly off of the function, and that's the vertex. So let's do a couple of problems first, one of each, one with the standard form, one with the general form. Find the vertex. Okay, so number one, find the coordinates of the vertex for the parabola, which is the graph, defined by this particular function. Now, our sort of generic model for standard form is f of x equals a, parentheses, in this case, the a is the negative 2, okay? X minus h, parentheses squared, plus k. All right, so once you have it in standard form, your vertex, you simply just use the numbers that are explicitly given in the function, the h and the k. And that gives you your vertex. Is this original function here for this problem, is that in standard form? Well, not exactly, not exactly. The problem is you got to be really careful with the signs, right? If there's a plus, it's got to be plus. If there's a minus, it's got to be minus. This plus is fine, right? We got a plus 3, that's our plus k. So 3 is what we're using for the k. Now, the problem is we have a plus 1, not a minus 1. Right, so we have a plus sign here in yellow. I'm looking at a plus sign here and a minus sign here. That's a problem. That's a problem, but it's not a big problem because we can very, very easily write that as x minus something. So we could write f of x, and this is what you have to do here, equals negative 2, parentheses. Now, instead of x plus 1, we have to write x minus. You can't just change a plus to a minus and say minus 1. That's a different function altogether. But we could write x minus a minus 1 squared plus 3. Okay, so let's see what I just did. And we want to make our problem look like this model of the standard form. So what I did was I took this plus 1 and rewrote it as a minus 1. Two minuses is the same as a plus. So now the reason I did this is because, let me use a different color than blue. This is, or actually no, let's just connect this to the model. A is negative 2. H is the number after the minus sign. There has to be a minus sign. And H is the number that comes after the minus sign. So H is -1. K is the number that comes after the plus sign. So you need a plus sign out there. So K is equal to 3. So once you have a number times parentheses, x minus a number squared plus a number, once you have your function sort of set up in the same way, the same model as this standard form, you've got your vertex. So the vertex of this parabola is the point h comma k, which is -1 comma 3. So that means if you were to graph this, you would start at the point -1 comma 3, and then you would draw a parabola from there. In this case, it would be pointing down because you have a negative out front. But here in this problem, we're just looking at the vertex. So that's standard form. The next problem, same question. Find the vertex of the parabola, but now we have general form. Right? So f of x equals a x squared plus bx plus c. We call this general form. So for this particular problem, the a is a -1 because we have -1x squared. The b is the -4. Okay? And the c is the 6. So we have a, b, and c in this problem. A is the -1. We have -x squared. B is the -4. C is the +6. And in general form, your vertex is the point -b over 2a, comma, f of -b over 2a. We're using this function notation that we've been using throughout the entire course. Okay, sometimes things look a little bit more complicated than they actually are, right? So the vertex is a point. So there's an x and a y, right? It's an x and a y. The x coordinate of the vertex is -b over 2a, which in this case, -b, so that's negative of a -4. So that's 4 over 2 times a. A is -1. So 2 times a -1 is a -2. 4 divided by -2 is -2. So that's half your answer. All right, we're looking for find the coordinates of the vertex. So our answer is going to be -2 comma something. So what this f of -b over 2a means is it just means take that -2 and plug it into your function. F of -2. So instead of -x squared minus 4x plus 6, you go back to your original function. Let me highlight this so everyone knows what I'm talking about here. This is our original function. And we're plugging in 2 in for x. So -2 in for x. So -x squared, well, x becomes -2. So that's negative of a -2 squared minus 4 instead of 4x. It's 4 times -2 plus 6. Okay, see if we can simplify that. -2 squared. So -2 times itself is 4, positive 4. We still have a negative on the outside, so that's negative 4. Minus 4 times negative 2, so that'll be minus a minus. That'll be plus 8. And then there's still a plus 6 there. Negative 4 plus 8 is a positive 4, plus 6 is a positive 10. So that's what this f of negative b over 2a business is. It's just take your x value that you find first. All right, we do this one. Let me do it up here. We do this one first, get that answer, and then plug it into your function. Do that second. So the vertex of this parabola is negative, is the point, negative 2 comma 10. So to graph this parabola, you would start at this point. Let me circle it in green because that's the answer to this problem. You would start at this point and you would graph a parabola from there. Okay, so that is the vertex. You find the vertex one way if you have your function in standard form. You find your vertex a different way if you have your function in general form. Now we can talk about using that and extending that to the larger problem of making a graph. Making a graph. So now these are all components that we've talked about at various points in our semester. So use the vertex, which we've just talked about. And the intercepts, those are things we've talked about previously. The x-intercepts, possibly plural. The y-intercept, there's never more than one of those. To sketch the graph of the function, give the equation for the parabola's axis of symmetry. And then use the parabola to identify the function's domain and range. So there's a lot going on here. Some of these things are things we've talked about, explained, used in the past. We've talked about domain and range quite a bit. We've talked about intercepts quite a bit. We just started talking about vertex. So we're weaving together multiple things here. Okay, so let's start with the vertex. Let's start with the vertex. It's a point, right? It's a point x comma y, where the x is negative b over 2a, which in this case, well, let's see, what is a, what is b, what is c? A is equal to 1, because we have 1x squared. B is equal to negative 1, it's the number in front of the x, and c is equal to negative 6. So there's the a, the b, and the c. 1, negative 1, and negative 6. So negative b over 2a, well, negative b, so negative of a negative 1 over 2 times a, that's 2 times 1, which is 2, and there's our x-coordinate, 1/2. So now the y value, we take 1/2, the number 1/2, we plug it into our function. So that's g of 1/2. This is the g function in this problem, so it's plug 1/2 into the g function. So that's 1/2 squared minus 1/2 minus 6. Let me highlight this because we're always going back to this function. So for right now, I'm replacing the x's with the number 1/2. Okay, 1/2 times 1/2 is 1/4. 1 times 1 on top, 2 times 2 on the bottom, minus 1/2. So let's get a common denominator. We're going to need to in our next step. So that's 1/4 minus 2/4 minus, oh, went ahead. 1/4 minus 2/4 minus 24/4. I'm not going to spend a lot of time here talking about common denominators, but I multiplied the second fraction by 2 over 2. I multiplied the 6 by 4 over 4. Treated that 6, that whole number 6, like it was 6 over 1. And now we have a common denominator. So 1 minus 2 minus 24. That's, let me not try to squeeze that in. So that's a negative 25 over 4. Or if you like mixed numbers, that's negative 6 1/4, negative 6 1/4. So just under a 6. All right, so this is just a very similar to problem number 2. So our vertex is the point 1/2, comma, negative 25 over 4. Right? That's 1 point on the graph that we know. So let's come over to this graph. Let's see if we can figure this out. So this looks like 1 right there. So a half would be there. So we'll go down to 6 1/4. So it looks like right about there. Maybe I'll use green. All right, so that's the vertex. 1/2, comma, negative 25 over 4. That's 1 point on our parabola. Next in the problem, it says use the vertex and the intercepts. Use the vertex and the intercepts. So I'll start with the y-intercept, because that's always the easy one. The y-intercept. To find the y-intercept, plug in 0 for x. Plug in 0 for x. This is not just for quadratics. This is for any function. Linear, quadratic, rational, logarithmic, and any function. To find the x-intercept, you plug in 0 for y. To find the y-intercept, you plug in 0 for x. So the y-intercept, I think, is always the easy one. So g of 0 is equal to 0 squared minus 0 minus 6, which gives us a negative 6. Right? So that's pretty straightforward. When x is 0, y is negative 6. So there's 2 points. We have the vertex. We have the y-intercept. So now let's find the x-intercept. We don't have too much room on this screen, so I'll do the best that I can. Oh, not 6, 3. So we had vertex, then y-intercept. Now x-intercept. To find the x-intercept, plug in 0 for y. Now remember, the word intercept. An intercept is any point that contains the number 0. Any point that contains the number 0. So y-intercepts have a 0 for x. It's 0, comma y. The x-intercepts have a 0 for y. It's x, comma 0. And so it's an intercept. To find an intercept, you have to use a 0 somewhere. All right, so instead of plugging in 0 for x, we'll put a 0 in for the y, which is the g of x. So 0 equals x squared minus x minus 6. And it looks like this one we can factor. X squared minus x minus 6. This factors to x minus 3 times x plus 2. So we're doing a little bit of factoring here. And now the zero factor theorem says, well, if these two things multiply together to give you 0, either x minus 3 is equal to 0, or x plus 2 has to be equal to 0. One or the other. So we have to consider both. So x is equal to 3. That's one x-intercept. And if we subtract 2 from both sides, x is equal to negative 2. That's the other x-intercept. So they're actually points. The x-intercept is when y is equal to 0. So we've got the point 3, 0. That's a point on the graph. It would be about right here. 3, 0. And then the x equals negative 2, that's actually the point, negative 2, 0. So we'll go over to negative 2, and there's another point. Negative 2, 0. I'm going to graph it in. Let's see, something that really pops. I'll use red for the graph. Here's the vertex. So the parabola is going up like this to this y-intercept, up to this x-intercept, and it does something like that. Now, the axis of symmetry. We've already figured that, we've already done the work for the axis of symmetry. Now let me use orange. I'll use orange for the axis of symmetry. It's the line that cuts the parabola up into two equal halves, two identical halves. So this green line is the axis of symmetry. It's not part of the graph, right? The graph is red. The graph is the red one. The orange one, that's the axis of symmetry. It's like the center line of the graph. It's a vertical line, and it always goes through the vertex. Vertical lines have an equation x equals a number. And for parabolas, for quadratic functions, it's always going to be x equals the x number from the vertex, which we did first. The vertex is the point 1/2, comma negative 25/4. So the axis of symmetry is the line x equals 1/2. That's a line. It's a vertical line. And then for the domain and range, it's the last thing we need to talk about, the domain. Well, the domain is the set of all x values associated with this graph, or the set of all x values you're allowed to plug into this function. The domain of every polynomial, not just quadratics, but every quadratic function, and more generally, every polynomial function. The domain is all real numbers. There is no number that you're not allowed to plug in. Right? Every x value works. So the domain of the function, and I'm really running low on room here, so I'm going to go to the top. The domain, this is not something you even have to think about. Domain is negative infinity to infinity. Right? If you look at my written solutions that I have posted on my website, they'll be much more linear, starting at the top and then working down, down, down. I'm running a little low on screen space here, so I'm having to sort of circle back to the top. But the domain is always negative infinity to infinity. Right? There's no issues with any numbers being plugged into this quadratic function. The range, on the other hand, I'm going to use a highlighter. I'm going to use, let's go with a blue highlighter. The range is all the y values associated with this function. Oh, I didn't want to do that. The y values. Oh, that's a little bit dark. Let me go green. Okay, the range is all these y values that appear in points on the function. It's always going to start or end with the vertex. That's why I say you've already done all the work involved. Now we just have to state the answer. So the range of this function, it'll be from it, since the parabola opens up, the range starts with the vertex and then goes up to infinity. So it's either going to be parentheses negative infinity to vertex. Well, let me say, be more specific. The y from the vertex. Or it's going to be the interval. This is interval notation. The y from the vertex, comma, infinity. So it's either from the vertex up, or if the parabola is pointed down, it's negative infinity up to the vertex. In this problem, we're starting with the vertex and going up. So the range of this function would be the negative 25 over 4 up to infinity. Negative 25 over 4 up to infinity. So once you have the vertex, that tells you the axis of symmetry from the x value. That tells you the range from the y value. Okay, and like I said, for the written solutions, go to my website, look at the written solutions there. It's much more clear. I used multiple pages. I didn't try to squeeze everything onto one page. Okay, so what I'm going to do here, the next problem is the last problem. So it's part A, B, and C. So this is a modeling problem, a word problem. I am going to stop this video now and pick up on number 4. My very next video will be this video will be labeled part 1. And then in the next video, part 2, I'll talk about problem number 4. Okay, that's it for now. I hope this was helpful.